Calculus section 6.1 on the law of sines. The question we're going to look at is what are the different methods that can be used to prove congruent triangles? So there are 5 methods if you think back to geometry. We have side, 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 angle, side, angle, side, angle, 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 side, as well as the right triangle case of HL. And if we are given this much information about a triangle, not only are we able to prove it to another triangle with that same information, but we can solve it. In other words, we can find all of the sides and all of the angles in that triangle. To do that, we're going to use the skill with the law of sines. This original triangle is not a right triangle. However, if we drop down this altitude, we can call it H. What that does is create 2 right triangles for us, this yellow right triangle and this light blue right triangle. And in this triangle on the left, I see that this angle A is original to the triangle, this little b is original to the triangle, and then this h is the entire length. However, this little fraction down here is not the original side C, and this is not the original angle C, so we don't want to use them. So using this important information from the left triangle in yellow, we could say that the sine of A is equal to opposite over hypotenuse. Likewise, in this light blue triangle on the right, we know this is the original angle B. This is the opposite. This is the original little a. So we could say that the sine of B is equal to opposite over hypotenuse. H and A might look confusing because H is this side. It doesn't stand for the hypotenuse. We have these 2 different trig functions. I noticed that in both of them there is the letter H. So in this one on the left, we can multiply both sides by little b to get H by itself. And for this one, we can multiply both sides by little a, get h by itself. Then by a transitive, since they're both equal to this little h, we could say that b times the sine of a is equal to a times the sine of b, which is a nice equation. It doesn't have the letter h in it anymore, and it only has the letters of b and a. We're going to go one step further here. Divide both sides by little b. Also divide both sides by little a, so those cancel out, and we get this nice formula where we have the sine of a over a is equal to the sine of b over b, and that doesn't use h, so this extra line that we drew in here is irrelevant, and I can go back to the original triangle, that non-right triangle, and say that the sine of a over a equals the sine of b over b, and if I had drawn a different altitude, we could have also had these 2 fractions equal to the sine of c over c. So this law of sines will work for any triangle regardless if it's a right triangle or not. First example, we have triangle ABC that we're trying to solve. We're given angle A, we're given angle B, we're given little a, we need to find little b, little c, and angle C. To start off with, I know there's 180 degrees in a triangle, so if I take 180 minus both of those, then angle C is 50 degrees. To find little b, we could say that the sine of 70 degrees over 7, that's sine of a over a, is equal to the sine of 60 degrees over little b, that's sine of b over b. Cross multiply here, b times the sine of 70 is equal to 7 times the sine of 60. One more algebraic step, we're going to divide both sides by the sine of 70. And then this is a calculator problem. Take 7 times the sine of 60, divide that by the sine of 70. And that comes out to a length of about 6.45. One thing that I noticed about this is it makes sense because 70 degrees is bigger than 60 degrees, 7 is bigger than 6, so that is all consistent. To find little c, we'll go back to the law of sines. The sine of c, which is 50 degrees, over little c that we don't know, is equal to, I could use a or b. A is a better option because those are both exact, so we'll set it equal to the sine of 70 degrees over 7. Like we did in the last one, we're going to cross multiply now. b times the sine of 70 is equal to 7 times the sine of 50. And also, like the last one, we're going to divide, get that c is equal to 7 times the sine of 50 divided by the sine of 70. So that's another calculator problem. We'll punch it into our calculators and come up with little c at about 5.71. For all of the sides, if we have to round them, we round them to 2 decimal places. If the angles have to be rounded, they're to the nearest tenth. But now the triangle is solved, we know all of the angles and we know all of the sides. Next problem, triangle ABC. Don't have little a, don't have little b. This is the information that we have. Like the last one, I can subtract these angles from 180 to get that this angle is 30 degrees. To find little b, we have sine of 30 over 12 is equal to the sine of 130 over little b. And then if you cross multiply, divide both sides by the sine of 30. For little b, we should be getting about 18.39. I didn't show a lot of the work on the screen because I just went to my calculator. You would just cross multiply and then do the algebra like we did before. And then the next one, we could say sine of 20 over a is equal to the sine of 30 over 12. Once again, cross multiply and then divide to isolate it. Little a is about 8.21. Notice here that largest angle, largest side, smallest angle, smallest side, so everything is accurate. And there is the solved triangle. Then in your notes, there is one other example with an angle side. It gets into some side angle. I have another video link for that you can check out how to solve the side angle triangles, because those are a bit more confusing. We still use the law of sines, but the results are sometimes ambiguous. We do have one application problem to look at. We're not going to do the entire scenario, but we want to be able to draw this. It says a plane travels on a bearing of 80 degrees east of north for 4 hours at 300 miles per hour. So to do this, we'll draw in an x and y axis. Here is where the plane is starting at the origin. And it's going 80 degrees east of north. So it's not going straight north, it's rotating 80 degrees to the east of that. So the plane is going to look like it's going in this direction. Here's where the 80 degrees is at. And if it's traveling 4 hours at 300 miles per hour, 4 times 300 means that it's traveled 1,200 miles, if I know that distance. It then changes course to 40 degrees east of north for 2 hours at the same speed. So when it changes course, I'm going to put a new origin, a new y-axis, a new x-axis. I'll change the color here as well. And now the course is only 40 degrees east of north. So instead of looking straight north, we're going to rotate to the 40 degrees to the east of that. It's going to do something kind of like that. Our 40 degrees is going to be right there. And it's traveling at 2 hours at the same speed. So 2 times 300 miles per hour is 600. So we have this drawing. Eventually, what we'll be doing with this then is trying to figure out the total distance traveled from the very beginning, or we might try to figure out, if we draw this in again, what is the bearing of from the initial point to our final point, other things that we can do with that, using the law of sines, and then also using eventually the law of cosines. But that's it for this section of 6.1 notes.